So in this problem, we have a fuel tank, and I actually wanted to do this one because I've had a similar problem with one of my cars. And this fuel tank has a little vent in the top, right there. And the rectangular tank is vented to the atmosphere, and a pressure transducer is located in its side. Okay, so we're going to assume that this is the midline for the tank, so it could be filled that much, for instance. And we have a pressure transducer down here that's basically a sensor that translates the pressure into an electrical signal that your car can read. Okay, and we're going to say that this distance is 0.5 feet. Okay, so the transducer is half of a foot below the midline of the tank. Okay, and we're going to treat any measurements below this midline as, we'll call this Z1, because what we want to look at is as the car accelerates, the fluid kind of behaves like a rotating body, if you want to think of it that way. Or it's going to behave like a body that kind of shifts, okay? And what could happen is if the car is accelerating this way, we're going to call this AY. What's going to happen is because of inertia, the fluid's going to want to back up against this back wall. And if the acceleration isn't too fast and there's not a lot of sloshing, we can kind of think of it as it's going to stay at this midpoint here, but it's going to kind of end up with a slope on the surface. Okay, so the question is asking us, first of all, to determine an expression that relates our acceleration to the pressure that the transducer is experiencing, because remember, as this fuel level goes lower because of the acceleration of the car, the pressure on that transducer is going to reduce. Okay, as the pressure reduces, it's going to think that there's less gas in the car than actually is. Okay, and this does happen. I actually, like I said, I had a problem with a car, and what was actually happening was it said there was more fuel in there than it was because of when you would because of acceleration or something with the placement of the transducer. And then when I went down a hill, the tank would tip and it wouldn't sense properly, and it wasn't draining properly, and I ended up, my car would stall out until I could get it filled up again. So I actually had that happen in real life. So we want to first of all, again, find an expression that relates the acceleration to the pressure that the transducer is reading. And then we want to find the maximum acceleration that can occur before the fuel level drops below what the transducer is reading. And then the reason we want to be concerned about that is because at that point, your car will probably tell you you're out of gas when you're not actually out of gas. But if that transducer is right next to the fuel line, then that could be a problem, because that could also, mean that there isn't any gas going into the fuel line, even if you have gas. So, okay. So, back when we started talking about the equation of motion for a fluid, I said that it would work for either a stationary fluid or a moving fluid. So the equation, if you don't remember, is our gradient of pressure minus gamma times k hat is equal to the density times the acceleration. So remember, this is basically just F equals ma, only we're doing it for a fluid, right? Because we have to worry about density and not mass. Okay, so remember that this is really three equations. We have one in the x direction, one in the y direction, and one in the z direction. Okay, so what those equations are is, well, negative derivative of pressure with respect to x is equal to the density times the acceleration in the x direction. We've got the negative derivative of the pressure with respect to the y is equal to density times acceleration in the y direction. And then we have that pesky gravitational factor in the x direction, so we've got that the partial with respect to, partial of the pressure with respect to the z component is actually equal to gamma times plus density times acceleration in the z direction. Okay, now in the picture, we're going to treat our coordinate system as x is coming out of the board, which so we can kind of ignore it because we're assuming symmetry, or that our cross section is the same at all x. Y is pointing to the right and z is pointing up. And so in this picture, only y and z are actually changing. Okay, so I'm going to kind of do a little bit of funny math here, and I'm going to say that my change in my pressure is equal in the y direction to minus the density times the acceleration in the y direction times the change in height, right? And in the z direction, well, we've got minus gamma plus rho a z times the change in the height. Sorry, I guess this would be change in the y direction, and this would be the change in the height. Okay, so we can kind of look at the left-hand side and the right-hand side and just kind of ignore for a moment that we even were looking at pressure at all. And we can say that, well, this side has to be the same thing as this side. Otherwise, they wouldn't both be equal to pressure. So we're going to write it out this way: minus rho times the acceleration in the y direction times the change in the horizontal position is equal to gamma minus density, plus density times acceleration in the z direction times the change in the height. Okay. Now, we can use this to see how the depth will change with the acceleration, because we have this acceleration term here. And so what we're going to do is we're going to look at the slope of that line that's created, this one right here, as we accelerate it. Okay. So we want to know about the rise over the run, which is, slope. And we can solve for that, and that's going to end up giving us this equation. My minus signs cancel out, so we can ignore those here. Okay. Well, remember that gamma is equal to the density times gravitational acceleration. So if I write that out like this, we're going to have a density in every term, which isn't terribly helpful, so we're going to get rid of it. So, y is equal to the acceleration over gravitational acceleration plus the vertical acceleration. Okay. Well, in this case, our car is not moving up or down, so it's not accelerating in the z direction, so we're just going to set this to 0. And so that means that our rise over our run, which we could also write as delta z over delta y, is going to be equal to the acceleration of the car in the y direction over the gravitational acceleration. Okay. So in this case, our gas tank is 1.5 feet wide, and we're treating this half point 1.5 feet. And so if we want to think of rise over run, our run in this case will be 0.75 feet. Okay. So delta z will be equal to ay delta y over g. So that's going to be 0.75 feet times ay over g. Okay. Now we want to think about the pressure here. So how much is the pressure that the transducer experiences based on this change in height, right? So the pressure at the transducer is going to be gamma h, right? Well, in this case, that means it's going to be gamma times the difference between that delta z, which we talked about here, and that's 0.5 feet. Okay, so we're going to have 0.5 feet minus delta z. Okay, we can substitute the expression we just found for delta z. So that means we're going to have gamma times 0.5 feet minus 0.75 feet times ay divided by g. Okay, so this is the expression we can use. If we want to plug some numbers in, we can say 0.65 times g, which is, sorry, I think I wrote something down wrong. I think it's 32.2 feet, pounds per feet cubed. No, sorry, can't use that eraser. Sorry, I think the book wrote something, pressure times area. I think the book wrote something wrong down here, so I'm going to leave that for a second. Okay, so if we're looking at finding the limiting factor, we want to know basically what we're going to be looking at is what are we going to do here if how do we basically find when the transducer is 0, right? And so if the transducer is getting a 0 reading, that means this term has gone to 0. If the pressure has gone to 0, it's because our level has changed such that the top of the gas is at the same level as the transducer. So we're basically going to set this expression to 0, 0.5 feet minus 0.75 feet. Okay, and we're going to look for what that acceleration is. Okay, so we're going to have 0.5 feet is equal to 0.75 feet times ay over g. I'm going to solve for ay. So ay is equal to 0.5 feet over 0.75 feet. And then we're going to multiply that times g, right? Okay, so basically our acceleration cannot be more than 2/3 of the gravitational acceleration, which is actually 6.54 meters per second squared, or if you're working in British gravitational units, it's 21.5 feet per second squared. Okay, so it can't be any more than that because then our transducer won't have any fuel to read. Now, the other thing to keep in mind is that when we're doing problems like this, or when we're thinking about doing this, if we were to build an actual car with a pressure sensor in it, that pressure sensor is reading a current or something like that, or a voltage difference, and we can measure that. And at the same time, we should have a computer in the car so that we know how fast it's going. And so we can take into account and calculate how much liquid actually is in there based on the acceleration. And so if the pressure transducer is reading a low value, we should be able to calculate a correction. Okay, so that's why it's important to know these things, is that way we can equate this sort of thing with what the car's computer is reading about its acceleration and make sure that everything matches up.